Hello everyone, my name is Aarohi and welcome back to my channel. So guys, before we start today's lecture, I just want to remind you all that please like, share, subscribe and comment. Please show your support by liking and commenting because it helps me understand whether the content which I'm preparing is helpful or not. And I put a lot of time in making these videos, so your support really motivates me. So please do that. Now let's start today's lecture. So guys, in our last two classes, we learned how to create an LLM from scratch. And during that process, I told you that we are using the transformer architecture, but I didn't explain you the transformer architecture at that time because I wanted to cover that separately. And today we are finally going to do that. We will learn about transformers because all modern LLMs are built using the transformer architecture only. And if you want to create your own LLM from scratch, then you should learn this concept. So let's begin. So guys, the very first paper on transformer was Attention is All You Need. Okay, let me open that paper first. So this was the paper, Attention is All You Need. This paper was released in 2017 by Google. And if you will scroll this paper, come to the section where they have uh, shown us the figure of transformer architecture. So this is the architecture of original transformer model, the very first transformer model. And if you'll see here, we give input from here, then there's an embedding layer, we are doing position embedding, and then this block over here is a encoder, and the block over here is a decoder, right? So these are the main points of this paper, this embedding layer, position embedding, encoder, decoder, multi-head attention layer, right? This was the main focus of this paper. And nowadays, the modern LLMs, they don't use this encoder part. They work with only this decoder part only. So I have told you that LLMs use transformer architecture. And now what I'm telling you is they don't use this encoder part of the transformer architecture. They only use decoder part of this transformer. This concept was first introduced by OpenAI when they introduced GPT-1 LLM. So GPT-1 was the first LLM which was built on decoder only transformer. This part of the transformer. Okay. It was not using encoder part, it was only using decoder part. And GPT-1 was the first decoder based transformer. And this is the paper of that. OpenAI released this paper. And in this paper, GPT-1 was discussed. And here, if you'll scroll down, just go to the section where they are talking about model. Let me see. Let's scroll down. Okay, under this model specification, let me just see. Under model specification, our model largely follows the original transformer work. We trained 12-layer decoder only transformer. See, they're not using encoder. This encoder part they're not using. They are only using decoder, and then they have discussed here other layers which they have used. But the main thing is that they have used the transformer, but they have used only decoder part. Okay, so this was the first paper, and then they released GPT-2, which was again decoder only transformer. And then they released GPT-3, again it was a decoder only transformer model. And let's talk about other companies. Let's talk about Meta. So Meta released LLaMA LLM, right? So that LLaMA LLM is also a decoder only transformer. So what we understood till now, that almost all the modern LLMs are based on the transformer architecture, but they do not use the full encoder decoder structure. They only use the decoder part of the transformer. Now guys, before we discuss about the decoder only transformer in detail, we should first understand the original 2017 architecture, which is this. We will understand both encoder and decoder in detail, and after that we will understand the decoder only transformer. So let's start. So if you'll see this architecture, the first thing is input, and input is going to the input embedding. Now let's see what all steps we will perform on the input before giving it to the input embedding. Suppose this is our input sentence. My name is Aarohi and I love coding. Now, this sentence will first go to the tokenizer. Here, we are going to have a tokenizer. Tokenization simply means that we will split this entire sentence into small tokens. For example, we will have my as one token, name as another token, then is will be the next token. Like this, we will have all these tokens. This is the first task of the tokenizer. Then all these tokens, these are tokens now, all these tokens will be converted into some sort of IDs. So for example, for my, we got ID 103, and for name, we got ID 97, and for is, we got ID 86. So like this, we will have unique number for each token. So this is the first step. We will have these unique IDs for all the tokens, and this will go to the input embedding. Okay, let me just scroll down and show you. See, this is our input sentence. My name is Aarohi and I love coding. And after that, we used tokenizer on it, and tokenizer gave us tokens like this. So this is the first job. First job of tokenizer is to give tokens like this, and then it will convert them into some sort of IDs, and these are unique IDs. For each token, we are going to have a separate ID. Now this over here is the output of tokenizer, and this will go to the input embedding. Which input embedding? This over here, input embedding. What will be the input to this input embedding? This will be the input. This will be the input to that input embedding. Now we have entire sentence as IDs numbers, right? Now, why we did this step? Because transformer model expects number, so tokenizer prepared those numbers. And next step is input embedding. Now, why input embedding is needed? Because right now still we have the numbers, but these numbers your transformer will not understand. So we have to convert these numbers into embedding vectors. Now let me explain you this part in detail. So here we take each token ID. For example, this 101, which represents my word. We took one token ID, and then we prepared a vector for it, and you'll see that we have various numbers in it. How many numbers we are going to have in it, that part I will discuss in some time, but for now just understand that for each token, for each ID, we are going to have a embedding vector, and this embedding vector will be learned during training. So guys, we will understand this whole thing in detail today, so just keep watching and try to understand. So let's try to understand with our example only. So the example sentence which we used, my name is Aarohi and I love coding. Let's take the example of this. Let's take the same example. So my word will have this embedding, right? My is the first token which we converted into this unique ID 101 using a tokenizer. Then we have this embedding vector for it. This embedding vector. Embedding vector simply means we are going to have multiple floating point values in this embedding vector. How many values we are going to have, that part we will discuss in some time. So same for name token, we are having a embedding vector like this for is Aarohi and I love coding. For all these tokens, we are going to have embedding vector like this. Okay, and the length of embedding vector will be same for each token. For example, if there are 768 values in the first embedding vector, then in all the embedding vectors you are going to have the same value, same amount of numbers in all the vectors, and these vectors are called embeddings. Okay, this is what we are discussing over here. These vectors are called embeddings. So now the sentence will become like this. See on this side, e underscore my, what it means? It means the embedding vector of my word. E underscore name means embedding vector which we have for name token. E underscore is mean embedding vector for is token. Then embedding vector for Aarohi and I love coding. See, we have embedding vector for each word over here. And See, we stacked these words like this. Why? Because for each word, we are having a embedding vector. So let's say the embedding vector, this embedding vector, which is the first word, first token is my, and now we converted this my into this, and then we converted this into a embedding vector, and we have so many values over here, right? So let's say we have 5 and 2 values over here for each vector. Value part we will discuss in some time, like how we are going to have these many values, why we are choosing this number. That part we are going to discuss in some time. And this is for my word. We have this embedding vector. Okay. Then second word is name, and for name, token ID is 223, and for name we have this embedding vector. Okay, there are some values over here, floating point values, and the values, number of values will be same. So third token is we got this ID from tokenizer for is. So after that we convert it into an embedding vector like this. So we are going to stack multiple embedding vector for each token like this, and this is how your sentence will look like. Here what we are understanding, that token will have a single embedding vector like this. This is a token. One token will have a single embedding vector. But if you are working on a sentence have multiple tokens, right? Here we have so many tokens for single sentence. Then this is how your sentence will look like, where you are stacking the multiple embedding vectors. Now guys, let's understand how many values we are going to have in a embedding vector, right? I have told you that every embedding vector will have a few numbers, and the size of embedding vector for all the tokens will be same. But what should be the value of embedding vector, each embedding vector? How many values we need in each embedding vector? Let's discuss that part. So guys, in transformer based models like GPT or BERT or any other such model, the embedding length is defined by this D underscore model. Okay, this D underscore model. If you are using D underscore model 256, that means the embedding vector will have 256 values. And if you are writing D underscore model is equal to 512, then you are going to have 512 values, floating point values in each embedding vector. Means for my token, when you convert it into ID, after that you are converting into embedding. That embedding will have floating point values. And if the D underscore model is 256, that means you are going to have 256 floating point values in the embedding vector for that token, or for all the tokens which are there. For coding also you are going to have 256 values. For love also you are going to have 256 value. And for I also, the embedding vector which you are going to create for I word, I token, that will also have 256 values. Okay. So that value depends upon which parameter, this D underscore model parameter. And guys, GPT-3 model, if I talk about GPT-3 model, GPT-3 model have 4096 value over here. D underscore model is 4096, which means the embedding vector, each embedding vector, like for this embedding vector will have how many values? 4096 value. This embedding vector will also have same value, and every vector for each token you're going to have same number, 4096 values. So this we define while creating the transformer. When you'll write the code for your transformer, over there we mention this, and when we will write the code for transformer, there I will show you what we understood over here, that every token gets the exact length of embedding vector. Every token will have if over here the value is 512, D model is 512, then every token will have 512 values in it. Now the next question is, what we are going to have in these embedding vectors initially, means when you'll start training your model, when when you have just started the work, initially what values you are going to write over here, because I have told you that for every embedding vector you need 512 values. For example, the D model is 512. That means for every embedding vector, right, the tokens which you have in your sentence, these tokens, for these tokens you're going to have a separate embedding vector, and the every embedding vector will have 512 value if the D model is 512. Now, what kind of values you will write there initially when you just started the work? Because with time, these values will be learned. What will be the values over there initially? Okay, so let's understand this part. So, initially, those embeddings are just filled with random values. You will use Gaussian or uniform distribution for that. Okay, so again, when we will code, there I will show you how to write the code for it. Now just understand the concept that initially the 5 and 2 values which you are going to have in each embedding vector for your tokens will be random initially, and we will give those random values using Gaussian or uniform distribution. So for example, you can see here, for my, suppose we have this embedding initially. Okay, so we have 5 and 2 values over here, but right now I'm just showing you 3 values, and we have 5 and 2 values in this embedding vector. And the name token also, we have 5 and 2 values, and I'm just showing you first 3 values right now. So now initially these values are random, so these numbers mean nothing at the start. Training will shape them into meaningful vectors. Guys, remember, these embeddings are learnable parameters. This is very important to understand, that the embeddings which you are going to have for each token, embedding simply means this embedding vector for each token, these embeddings are trainable parameters. So the numbers over here are called parameters. Okay, so these embeddings are trainable parameters, means like just like weights in a neural network. You know that in neural network we have weight, we update the weight, we train the model, we update the weight. So like this, these embeddings are also trainable. So to understand this, let's first understand what is vocabulary size, because you need to understand the meaning of vocabulary size, then you will understand this concept properly. So vocabulary size simply means total number of tokens your tokenizers can produce. So for example, what we get from tokenizer over here, so these are the different tokens which are tokenizer produced, right? So vocabulary simply means total number of unique tokens that your tokenizer can produce. But remember that tokens are not words. Tokens can be words, subwords, characters, punctuation, special tokens. Okay, so for example, this Aarohi word over here, suppose the tokenizer which you used, it divided this word like this: double A R as one token, and then Ohi as one token. So I'm talking about these tokens. So right now over here, tokenizer tokenized it properly. It Aarohi as a one word, Aarohi as a one token. But sometimes some tokenizer can split this Aarohi into two parts like this also. Okay, so this is what I'm saying. And let's suppose if there is a full stop after the sentence, then that full stop will be considered as single token. And if there is any other punctuation, that punctuation can be treated as a separate token. So this is what I'm saying. Vocabulary means number of tokens. Okay, not number of words, number of tokens. And tokens can be words, subwords, punctuation, special characters. And suppose if your tokenizer, here I'm just showing you single sentence. Now imagine if your tokenizer, the tokenizer which you are using, okay, let's say that tokenizer have 50,000 tokens. 50,000 tokens. That means the vocabulary will be, what will be the vocabulary then? Vocabulary will be 50,000. Suppose the tokenizer, you provided your dataset, raw text to it, and it created 50,000 tokens. Those 50,000 tokens will be the vocabulary. Okay, vocabulary simply means the unique words. Now, that means your input embedding layer, what it will do? It will create for all those 50,000 tokens. For every token, you will have a 1D vector of length 512. Why? Because we have defined D model as 512. If you'll define the D model as 256, then you will get a 1D vector of size 256. So, depending upon the vocabulary, if the vocabulary is 50,000, you will get 50,000 1D vector of size D underscore model. If your tokenizer gave you 30,000 tokens, unique tokens, so that means the vocabulary is 30,000. Your model know about 30,000 different words. Then you will get a 30,000 embedding vectors, one embedding vector for one token. Finally, in embedding layer, what you will have? At embedding layer, what will you have? You will have, suppose if the vocabulary is 50,000 and D underscore model is 512, then here you will have a matrix and the size of that matrix will be this 50,000 into 512. That means you will have 50,000 rows and each row will have how many values? Each row will have 512 values. So your embedding layer will give you a matrix, and that matrix is basically a table, right? Rows and column, a table. So embedding layer will give you a lookup table. We will discuss about it in some time. You just remember right now that the embedding layer will be a matrix, will be a table where you are going to have rows and column. Rows, how many rows you will have in embedding layer? It will depend upon the vocabulary size. If there are 50,000 tokens which your tokenizer generated, then you are going to have 50,000 rows. And if your tokenizer tokenized your dataset into 20,000 tokens, then you are going to have 20,000 embedding vectors. Each vector, embedding vector for each token. And the length of every embedding vector will be decided using this D underscore model. And if the D underscore model is 512, that means you are going to have 512 columns. One column is for one value, and all these values will be random initially, right? Floating point values will be there, and those values will be random. And guys, one more thing I want to address over here, that how does vocabulary size affect the model? Okay, so big vocabulary size means that it can represent more words directly. That means fewer unknown tokens, because if your model know lot of words, if the vocabulary is more, that means your model know more. If your model know more, that means you will have fewer unknown tokens, right? But in this case, if the vocabulary size is huge, that means you're going to have a huge embedding matrix, right? Huge embedding matrix means that training will also become heavier, right? And if the vocabulary is smaller vocabulary, for example, you have one vocabulary which have 50,000 tokens, and you have another vocabulary which have 10,000 token. So the vocabulary in which you have 10,000 token, that is smaller, right? So that means the disadvantage of smaller vocabulary will be that common words will be break into pieces, right? So let me tell you a few common vocabulary sizes which are used in real LLMs. So for example, GPT-1 model use 40,000 tokens, 40,000 vocabulary. Okay, the vocabulary of GPT-1 is 40,000, and the vocabulary of GPT-2 is around 50,000, 50,000, 200 something. Okay, and then GPT-3 also have similar kind of vocabulary. BERT model's vocabulary is 30,522, and then LLaMA model vocabulary size is 32,000 tokens. In the same way, Mistral have 32,000 tokens as vocabulary. Okay, so these are the different vocabulary sizes used by the different LLMs. Now the next question is, I have told you that embedding matrix will have embedding matrix. Initially there will be some random values, right? And these values will be learned during training. Now how these values are actually learned, now let's understand that part, how training happen, how embedding this embedding layer learn these embedding vectors. Because I have told you, right, that initially for each token you are having a embedding vector, right? But that embedding vector have random values. For example, if the d underscore model is 512, then I've told you that for each token, for my, you are going to have 512 random values. For name, you are going to have 512 random values. And in the same way, for is, you are going to have 512 random values. And in the same way, for entire vocabulary, you are going to have random values. And if there are 50,000 tokens in your vocabulary, that means you're going to have 50,000 1D vector, 1D embedding vector, which have random values right now at the initial stage. But when training starts, at that time, epoch by epoch, with time, these embedding values will make sense. And the embedding vectors which are similar, or they are which are closer to each other means which have semantic relationship. Okay, like India and Delhi, there is some relation in between it. Love and like, there is some relation in between it, right? So those kind of words will have a similar kind of embedding vector with time, with training, and these numbers will be learned. The numbers which are there, the 5 and 2 numbers which are there in each embedding vector will be learned. Now let's try to understand this concept, how that training happen. So guys, I have told you over here that the embedding layer will give us a matrix, and this will be the size of the matrix. The vocabulary size, let's say if the vocabulary size is 50,000 into 512, and this is basically the embedding dimension of each vector, right? And we have also discussed that each token ID will pick one row. One row means one embedding vector. Now the question is, what kind of code or what kind of concept we use in embedding layer? Because I'm saying embedding layer and we have discussed so much about the embedding layer till now, but what kind of code or what kind of concept we use to do this task? The which task? To get this matrix, to get the 5 and 2 value of each embedding vector learned. Okay, what kind of code we use for that? We are understanding that part now. So guys, first of all, learn one thing, understand one thing, that embedding layer is not a neural network layer. It has no neurons, it has no activation function, it has, we are not performing any kind of matrix multiplication over here. Okay, what we are doing, we are simply using it as a lookup table. Lookup table I have mentioned over here. Remember, lookup table simply means a big matrix of learnable numbers. Okay, why big matrix of learnable numbers? So I have explained you over here, and that if you have 50,000 tokens, that means vocabulary size is 50,000. That means you're going to have 50,000 1D embedding vector. Each you will have 50,000 rows. One row represents one token, and for one token we are going to have 5 and 2 values. That means you are going to have 50,000 rows and 5 and 2 columns if the vocabulary size is 50,000, and if the embedding dimension we have mentioned is 5 and 2. So this is a big matrix, right? So it is a lookup table for our model. And why we call it a layer then? Because I have told you this is simply a matrix and there is no neuron, no activation function. So why we call it a layer? We call it a layer in the sense that it has parameters to learn. So parameters simply means the number inside the matrix. Okay. And parameters are trained. Initially, I've told you those values are random and they learned during training, and it is the part of the model, but it is not a neural layer. It is just a list of vectors that model can update. So there is no computation happening here. We are just using it as a lookup table. Now let's see it with example. So suppose our token Aarohi. Okay, let's write it over here. Suppose we have one token with the name of Aarohi. Okay, and its token ID is 9871. And from where we got it? Tokenizer gave it, right? Tokenizer gave it. And for this, we have a 1D vector, embedding vector of how many values? 512 values. Okay, suppose this is the scenario. What does this mean? This means the row number, which row number? Row number 9871 of our matrix. Of our matrix, which we have in a embedding layer. We use the embedding layer, a lookup table, which we were discussing over here. This lookup table, where we have a matrix, which have 50,000 rows, and each row have these many numbers in it. In this matrix, suppose the token ID of Aarohi is 9871. So in this matrix, which have 50,000 rows, in that matrix, in row number 9871, we have this embedding vector which represents Aarohi token. And each number in that row, each number which you have over here is a parameter. Now I hope it is clear what is parameter. Parameter means each number in the row which represents any single token. What I'm trying to tell you over here is that why we call embedding layer is a layer if there is no neuron, no activation, nothing is happening over here. We are calling it an embedding layer because we have these parameters in it, and model learn these values epoch by epoch. Model try to update these parameters, these values for each token. Okay, so I hope this is clear now. Now let's talk about how these parameters are updated. Initially these values are random, but I've told you with training these parameters are updated. All the parameters for all the tokens in the embedding matrix are updated. But how does that happen? Let's understand that concept. So let's take the same example. Suppose your model is trained on your sentence, my name is Aarohi and I love coding. And at the step where the input token is love, the next correct token is coding. But let's say model predicted music at the place of coding. Now this prediction is wrong. So loss will be high. Loss value might be something like 4.21, 5.63, something like that. Now we know that loss is high, and our goal is, what is our goal? Our goal is to reduce this loss, because if this loss is reduced, that means your model is accurate. And if your loss is zero or close to zero, that means model is best at its work. So to reduce this loss, what we do? Model update the weight after every epoch, and for that model first compute how much each weight contributed to the error and how to change it to reduce the error. So this process is called backpropagation. Backpropagation simply means gradients flow backwards from last layer to the first layer of the model. So which in our case, if we are talking about this transformer model, so last layer will be softmax layer, and the second last layer is linear layer. Then we have feed forward network, then we have attention network, then we have embedding, right? So like this, from backwards to the starting. Okay, so when the gradients will reach the embedding layer, Over there, only the rows for the tokens in your sentence get gradients. What are the tokens in our sentence? These are the tokens. So, out of those 50,000 tokens which are there in our vocabulary, only these tokens will get the gradients. Okay, means out of those 50,000 tokens which are there in the model vocabulary, only the token which are there in our sentence gets gradient. Okay, so in our case, what it is, my name is Aarohi and I love coding. So these will get the gradients. So let's pick this love token for instance, because error happened over here. After love, we should get coding, but model predicted music. So that's why we are taking this, we are picking this love token. Okay. For this token, let's say the gradient computed, which gradient we computed, which gradient model computed is a vector. So for, let's say, the love token, the ID, the token ID for this is token ID 34. So for the gradient which is computed for this is a vector and these are the values in it. So this gradient says that embedding of love must move in this direction to reduce the mistake. Now model knows in which direction to move. Then we use optimizer. We can use optimizers like Adam optimizer or stochastic gradient descent optimizer or any other optimizer to update the weights. And optimizer, which optimizer use this formula, new weight. We want to calculate the new weight. For that we need old weight, and then we need learning rate, and then we need gradient, and we will apply this formula and we will get the new weight. So this happens for the embedding matrix rows. Okay, so that the words get better meaning representation. And guys, if you'll see the transformer network over there, we have attention matrices also, where we calculate query key and value weights. We have feed forward matrices also. So everything is updated. Okay, so after every epoch, all these things are updated. Attention weights are getting updated, feed forward matrices are getting updated, embedding matrices are getting updated. So everything is getting updated. So this is what training literally means. So now we are not talking about the attention weights right now or the feed forward weights right now. We are just talking about the embedding weights right now, because today we are understanding the concept of embedding only. So let's talk about the embedding weight updates right now, as we will discuss the other weights when we will reach that section of the transformer architecture. Okay, so E underscore new means to get the new embedding for word, for token. Why we need a new embedding? Because this is what we are doing now. This is what we are trying to do. Initially the embedding vectors will have random values, and we are model is trying to update these embeddings so that these embeddings, these numbers make some sense, right? So now after every epoch we want a new values in each embedding vector, okay, which represents each token. So to get a new embedding, let's say E underscore new is a new embedding. For that we will use old embedding. We are using the same formula, guys. E old means the old embedding minus learning rate into gradient. E old simply means the current embedding vector for token love, because we are talking about that particular token right now. So the E old, let's suppose for the simplicity sake, let's suppose the E old token have these values, and the gradients which we computed for this is this, and the learning rate is usually something like 0.0001. So we are using that, and we will apply this on this formula, these values. If we apply it, so just see the calculation over here. So we got these new values. Now this is the new embedding we got. Okay, so like this process happens for each embedding vector, because each embedding vector is there for each token. Okay, so this happens for right now. The change is very small. If you'll see here, the small change is very small. But guys, remember, training runs for billions of such steps, and we repeat for all tokens in the sentence, and after millions of update, the embedding metrics will become meaningful. So love word, let's say the love token will get close to coding, enjoy, like these kind of words, and my token will get closer to tokens like I. Aarohi token will get close to other names. So, and if there are function words like and, is, they will get clustered together. So this is how semantic meaning work. So let's conclude what we have learned till now. Okay, so first we use tokenizer. Tokenizer will split the raw text into tokens, and after that we have embedding layer. Embedding layer will first initially create the random embedding vector for each token, and the length of embedding vector depends upon the d underscore model. Okay. And after that, embedding will go to the transformer layer. And at the final layer, loss is computed for first epoch. Now, based on that loss, model will compute how much each weight contributed to the error and how to change it to reduce error. So this process is called backpropagation. Every model trains in this way only. So there is a forward pass and a backward pass. In forward pass, we train the model, we get the prediction, we calculate the error or loss. So for example, correct output is coding, but the model predicted music. So loss is high. Now the task of forward pass is done. And now we will use the backward pass, which is backpropagation. And in backward pass, based on the loss, model will see which weight caused this loss and by how much. This is done by chain rule of calculus. But guys, you don't need the math for today's class, so we are not discussing it. Just understand that every weight gets a gradient. Gradient means slope, and gradient tells how much the weight affected the loss and in which direction the weight should move, or how big the change should be, like these things. And guys, this is again a big concept to understand back propagation. If you want, I can create a video on it, but let me know in comment section if you want, because this is one of the oldest concept in deep learning and used in almost all the models when you want to train them. Let me know if you want the tutorial on it, because you should know the concept of back propagation if you want to understand what all steps you perform while training the model. Okay, and guys, remember, in the beginning model will not perform well because the embedding values are random, attention weights are random, feed forward weights are random. So the model will produce nonsense output, and back propagation will help these weights slowly to adjust to reduce the error. So guys, today we are discussing this much only. What we have discussed today, we have discussed about the input and the input embedding. That's it. Okay. And in my next video, I will cover the next topic. We will talk about position encoding and all these things in detail. Okay. So guys, please, again, I'm saying like, share and subscribe and comment if you like my content, so that I get to know that you like my content and I will create the videos more frequently. So I hope this video is helpful. And guys, if you have any suggestions, you can write down in comment section. And I hope this video is helpful. Thank you for watching.